So let's start in a place very familiar to all of us, slow function performance. This is your basic computer science 101 concept of performance. That is, you've written some code and it executes more slowly than you'd actually expect. Now, this often happens innocently enough. I mean, you're focused on creating some code chains that solve a particular problem in a particular way, but soon you realize that it's taking much longer to execute that code than you'd like. Now, the primary reason that code can be taking too long to execute has everything to do with how the language, and of course the associated hardware, is handling the execution of your code. For example, on some older hardware, which we will not actually name, executing a branching statement on a floating point comparison took almost 4x as long as doing the same thing on integers or booleans. The reason for this was the chip architecture. The part of the CPU dedicated to floating point calculations occurred after the branching logic stages, meaning that any floating point comparisons would have to wait until the end of the cycle pipeline, stalling the rest of the operations until it could finally execute its branching logic. But listen, don't freak out here. Modern hardware generally doesn't have these type of nuanced issues to deal with, but it does illustrate a very important point. How you write your code affects performance depending on how the language executes on the hardware, all the way down to how your silicon chips are actually structured. Let me be clear on this. To optimize your code, you have to understand the system that runs it. Now, slow function performance generally comes in two flavors. Firstly, you have your single slow function form. This is pretty straightforward. You've got some function that's taking like 2x or 50x longer to execute than you actually want it to. This is actually pretty easy to fix. I mean, you find the slow function, take a look at its code, figure out what the problem is, and then try a few fancy ways to fix it. Now, much harder to figure out is our second type. Death of 1,000 cuts. Effectively, this is when you have 100 functions, each taking 1 millisecond longer than it should, resulting in 100 millisecond extra in your overall program execution. This type of problem is the hard one to track down and even harder to fix because you usually end up slogging through every piece of your executed code to find small wins that in the end can make the difference between shipping and your company going under. Now, fixing these tiny performance problems is all about profiling. That is, timing your code to figure out what portions of it are running slower or longer than the others, and then making some small tweaks and then timing your code once again. And once you find one of the offending functions, you'll then need to start timing individual lines of code in that function and in all the functions that it actually ends up calling later. Now, this can get really gnarly unless you're an expert in the field, but fear not. The Android SDK has some excellent tools to help you track down these problematic portions of your code so you can fix them up right. Let's take a look.